Welcome to our video on sterility assurance, principles and practices. In this video, we will provide an overview of key concepts and principles involved in the preparation of sterile materials. We'll explore aspects of aseptic processing, terminal sterilization, facilities, equipment, and more to understand how microbiological safety is achieved in sterile product manufacturing. Sterility is defined as the absence of viable microorganisms. However, this absolute definition cannot be applied practically due to testing limitations. Microbiological safety is achieved through the implementation of interrelated controls that provide confidence in the suitability of items labeled as sterile. Controls focus on ensuring the safety of in-process or finished goods rather than just testing. Several factors influence the sterility of products, including facility design, equipment, materials, personnel, and procedures. Proper design and maintenance of facilities and equipment are crucial for sterility. The quality of ingredients and packaging materials also affects final product sterility. Personnel training and practices are critical, and well-defined procedures ensure consistent sterile production. Aseptic processing involves preventing the introduction of viable microorganisms into separately sterilized materials during assembly into a sealed sterile package. Key principles include maintaining ISO 5 conditions when materials are exposed, protecting sterilized materials from contamination, and executing process simulations to support batch or campaign duration. Terminal sterilization subjects products to a sterilization process that imparts a quantifiable safety level, achieving a probability of non-sterility of less than 1 in a million. It offers the lowest risk category for sterile pharmaceutical products, delivering measurable physical conditions corresponding to microbial lethality. Well-defined process parameters are strictly controlled within operating limits. Initial aseptic processing provides superior control over pre-sterilization bioburden. Subsequent terminal sterilization can use less aggressive conditions, minimizing product degradation. Combining the benefits of both processes extends the use of terminal sterilization to more sensitive products. Containers and closures are essential parts of sterile products, providing protection throughout shelf life. Key characteristics include reliability, maintaining container closure integrity, and compatibility with the product and sterilization processes. Selection criteria consider the absence of interaction, ease of handling, cleanliness, and protection of components. Decontamination reduces microbial populations without total kill and is used for bioburden reduction of materials, equipment, and environments. It includes sporicidal and non-sporicidal treatments. Depyrogenation minimizes pyrogen content, crucial for injectable products, and is used on surfaces, materials, and products to reduce pyrogenic contamination. Equipment in sterile manufacturing includes direct contact equipment like mixing vessels and filling pumps, which require stringent cleaning and sterilization procedures. Indirect contact equipment impacts product quality without direct contact. Other equipment, such as conveyors and balances, influences the manufacturing environment indirectly. All equipment must be designed for easy cleaning and minimal human intervention. Facility design must consider material and personnel flows, environmental controls, and cleaning, decontamination procedures. Critical aseptic processing areas are classified as ISO 5, supporting clean areas as ISO 6-7, and less critical areas as ISO 7-8. In classified areas include warehousing and administration. The goal is to minimize contamination risk and maintain appropriate conditions for sterile manufacturing. Active pharmaceutical ingredients should be considered for their origin and inherent properties. Excipients must be assessed for their potential impact on microbiological quality attributes. Process aids contribute to microbiological quality, including bacterial, endotoxin, and particulate contamination. Viable monitoring detects culturable microorganisms in air, on surfaces, and on personnel using active and passive air sampling, contact plates, and swabbing. Non-viable monitoring measures the number and size of particulates in the air, used for cleanroom classification and routine monitoring. Media fills use sterile growth medium to evaluate aseptic processing performance before new processes and periodically thereafter. Personnel perform essential activities but are also the most significant source of contamination risk. Understanding microbiology principles, proficiency in gowning and aseptic technique, adherence to procedures, and good personal hygiene are key. Regular training, demonstration of skills, and microbiological monitoring after aseptic operations are crucial. Sterilization processes are crucial for preventing microbial contamination in sterile product manufacturing. Steam sterilization uses saturated steam, radiation sterilization employs ionizing radiation, filtration sterilization removes microorganisms by passing liquids or gases through sterilizing grade filters, and gas sterilization uses gases like ethylene oxide. The choice of method depends on the product and packaging characteristics. Achieving sterility assurance requires a holistic approach, considering all supportive elements of operations. Process controls rely on validated processes rather than testing alone. Design and procedures must implement sound design, reliable equipment, and effective procedures. Personnel proficiency ensures proper training and adherence to aseptic techniques. These practices provide the highest level of confidence in the safety of sterile products.